Hi everyone, I thought this might be helpful to put together a video showing you how to solve problems like this with the ideal gas law and also the combined gas law. I'm just going to start with number one. This is on page 39, and just reading through this problem, we've got 100 grams of oxygen gas. Right away, when I see that we've got 100 grams or any kind of a quantity like grams or moles, we are going to have to use the ideal gas law because that is the gas law that includes moles. Okay, I'm going to set that up right now. All right, so I've set everything up here. First off, I solved for Kelvin because we were given degrees Celsius. Remember, Kelvin is the unit of temperature that is going to be directly proportional to kinetic energy. Okay, so we have to always convert to Kelvin. All right. Okay, we also have 100 grams of oxygen. All right, now this is oxygen, this is O2 gas. All right, so this is going to be 32 grams per mole, so that's going to be 3.1 moles. Remember, oxygen is a diatomic element. All right, so 3.1 moles. I put everything here in the equation PV equals nRT. We've got our pressure in atmospheres. We're solving for volume. 3.1 moles. Now, this is the ideal gas law constant that we need to use. I cannot stress enough how important it is to be aware of the units that you're using. Remember, chemistry, the units are more important than the numbers, okay? You've got to be thinking about units. This is the ideal gas law when we're dealing with atmospheres, okay? All right, so now what I've done here is set everything up. I want to show you how all the units are canceling that we need to cancel. Atmospheres cancels. Moles cancel. Kelvin cancels. Okay, what we're left is liters, and now we can solve for volume in liters. Okay, so I just did the math, and my volume comes out to be 50.6 liters. All right, this is using the ideal gas law to solve the problem. I'm going to go to another problem where we're at standard temperature and pressure, and I want to show you a shortcut to solving certain problems. All right, well, let's go to this one. All right, I'm looking at number 6 now. There's a shortcut that we can use to solve this problem because we're at STP. All right, what does that mean? We're at standard temperature and pressure. All right, this is always true for gases at standard temperature and pressure. 1 mole always equals 22.4 liters, okay? So we can literally just use this relationship to solve this problem. I'll show you how. Okay, so I just set this up. Since 1 mole for any gas at standard temperature and pressure is 22.4 liters, and we were given 0.475 liters, that comes out to be 0.021 moles of argon. Okay, argon has a molar mass of 40 grams per mole, so that's going to be 0.85 grams of argon. All right, now, this is a shortcut. This is a fast way to solve this problem. Although, I will tell you, you can use the ideal gas law to solve this. If you use PV equals nRT, you would come up with the same answer. I could just talk you through that right now really quickly. PV equals nRT. So the pressure is going to be, we could go with 1 atmosphere of pressure. Okay, so atmospheres. So 1 atmosphere of pressure. The temperature would be 273, and the volume is 0.475 liters. So that would be 1 atmosphere times 0.475 liters equals the number of moles, N, which is what we would solve for, times the R value. If we're using atmospheres, we would go with 0.0821, and that would be the R value when we're using atmospheres for pressure. And then the temperature would be 273 Kelvin. You could literally go through that calculation and you would still end up with this many moles of argon, and then you would calculate that many grams of argon. So again, we can use this shortcut because we are given the conditions of standard temperature and pressure. If we're not given standard temperature and pressure, then we absolutely must use the ideal gas law. Why don't we take a look at number 2 on this worksheet? I want to point some things out about number 2 before we jump into this. All right. So let's just read through this. We've got an air-filled balloon. It's got a volume of 225 liters. We're at a pressure of 0.94 atmospheres, and we're at 25 degrees Celsius. Soon after, the pressure changes to this. The temperature changes to that. What is the new volume? Okay, I want you to notice that there is no mention of any quantity in moles or mass here, okay? So we're not going to use the ideal gas law to solve number 2. We're going to use the combined gas law to solve number 2, all right? I'm going to set that up right now, and then we can solve it. Okay, so I just set everything up. I did all the calculations. You know, all you really need to do with these problems is just be very careful about units, okay? And just make sure that you're setting up, you're putting the right values into where the variables are in the equation. Just really be careful about that, and just be careful about the math. And if you solve this problem, you should come out with the answer that I got here. Our new volume is going to be 195.7 liters. All right, guys, just label everything. Be careful about units. It's really the key to doing any of this. Okay? Why don't we try one more? I'm just going to jump ahead to number 10 here, and I want to point something out. Okay, number 10, on page 39. What pressure is exerted by this many moles of a gas at 45.4 liters, and the container is at minus 24 degrees Celsius? Okay, so we're solving for pressure. Now notice they're not specifying what pressure unit we're using. We can choose whatever pressure unit we feel like using. If we want atmospheres, then we're going to need to use an R value of 0.0821 atmosphere liters per mole degree Kelvin. If we choose to use a pressure of kilopascals, then that's going to be 8.31 kPa liters per mole degree Kelvin. If we use millimeters of mercury, I honestly haven't memorized that R value, but we could look it up. Anyhow, I'm just going to go with a pressure unit of kilopascals, just to change things up a little bit. So I'm going to solve this problem. All right, so there it is. I don't know what else to say about it, but, you know, just make sure, again, that you are being careful about units, all right? Set things up, label everything, do the math properly, and you're going to do just fine, because really these problems are just what we usually call plug and chug kind of problems. You know, you just put numbers where they're supposed to be and do the math. It's terribly exciting. All right. Good luck, everybody.